Section 12.4, linear thermal expansion. So, have you ever had a jar and you've had a hard time opening it? Sometimes you just need to get a better grip and then you're good to go. But another trick you can try sometime is stick it under hot water and then try again. And assuming that it's not too slippery, if you dry it off first, you'll find it's a lot easier to open. Why does that work? Well, the key there is that when you stick it under hot water, the metal is going to expand more than the glass. And so you're able to then have an easier time opening it. It's not quite as tight of a seal. That's the idea of linear thermal expansion. You can have things change with temperature. So if we have, for instance, this rod, it's held at some initial temperature, T0. And then we increase the temperature by delta T, so that the final temperature is T0 plus delta T. What we would see is that that rod would also increase by some extra length. So that extra length we'll call delta L, so that the final length is the original length plus this delta L, this additional length. So what we see here is that by increasing the temperature, we can also lengthen an object that is going to expand as we increase the temperature. Now, what if we had two rods instead of one? Well, we can imagine if we had two rods and we increase the temperature, both of them would increase by the same amount, assuming they're identical rods. What if we then stuck those two rods together and increased the temperature? Well, each of the pieces of the rod should then increase by the delta L. And so if our rod is twice as long, we should get twice the change in length. In other words, how much the length changes is going to be proportional to what our original length was. So let's put all of these ideas together. How can we figure out how much the length of something will change as we increase the temperature? This is the linear thermal expansion of a solid. It says the length of an object changes when its temperature changes. And here we have the equation. The change in length, the additional length we gain, is equal to alpha times L0, the original length, times delta T, the change in temperature. This alpha is no longer angular acceleration. I'm sorry, we just don't have enough Greek letters or English letters. That is the coefficient of linear expansion. So it has to do with the metals. And we'll get to see an example of those various coefficients in the table in just a moment. So the common unit for the coefficient of linear expansion is 1 over Celsius degrees, or Celsius degrees to the -1, inverse Celsius degrees. And one note, why is this switched to Celsius degrees as opposed to degrees Celsius? So why do we go from degrees Celsius to Celsius degrees? This is a subtlety that I didn't pick up at first. We use degrees Celsius when we're talking about an actual temperature, and Celsius degrees is for a change in temperature. So that notes that we have subtracted two temperatures from each other. So technically the delta T here would be in Celsius degrees times the original length times this coefficient of linear expansion, which is in inverse Celsius degrees. So the inverse Celsius degrees would cancel the Celsius degrees, and we'd be left with just units of length from the original length, and that matches what we'd expect for the delta L, that the change in length would also have units of length, like meters. So let's take a look, like I said, at these coefficients of linear expansion. This is something you just get from a table, or it's stated in the problem directly. So here's a table that we have, coefficient of thermal expansion, and our linear is the one that we're focused on right now. The alpha, notice the units are given up here, inverse Celsius degrees. And so for all these various solids, we know the linear expansion coefficient. So if the problem mentions that you have an aluminum rod, you can go, oh, aluminum, that's a clue. You can know that you can look up its coefficient of thermal expansion. And you can see how various materials expand more or less, right? The aluminum expands significantly more than, say, glass. And that goes back to our jar example, right? The metal on the lid is going to have a greater expansion for the same temperature change as the glass underneath it. Right, and we will get to the volume expansion, which will allow us to also cover liquids, because liquids don't usually just occupy a single dimension of being linear. So for linear, we just focus on solids. All right, let's check out an example of this. Example 3, the buckling of a sidewalk. Concrete sidewalk is constructed between two buildings on a day when the temperature is 25 degrees Celsius. Sounds like a lovely day. As the temperature rises to 38 degrees Celsius, the slabs expand, but no space is provided for thermal expansion. Determine the distance y in part B of the drawing. So we want to figure out this y of how much vertically the sidewalks get raised as they buckle in the heat, because thermal expansion's real, right? If there's concrete slabs on either side of the houses, they can't expand outward if you don't have space allowed. So you gotta go somewhere. So I'm gonna go up here. So how do we figure this out? Well, we're gonna start by having to figure out how the length of the slab changes, right? We have the original length of the slab is this 3.0000 meters. Notice how many significant figures there are. This isn't going to be a huge change in length, so we need that extra precision. This is our L0. That's the original length. And it's the same for both of them. We want to know how much this changes as we increase the temperature from 25 to 38 degrees Celsius. And notice we don't actually care what the absolute temperatures are, just the difference between them. So the difference between them is going to be 13 Celsius degrees. All right. Anything else that we need here? Remember in that equation, there was the alpha, the thermal expansion coefficient. So that depends on the material. So what material do we have here? Here we're dealing with concrete. So let's take a look at that table that we just saw and see if concrete is included in there, because they don't seem to mention the coefficient in the problem statement. They do have concrete. Perfect. So concrete, third one down, so 12 times 10 to the minus 6 inverse Celsius degrees. Perfect. So that fills in our last piece of information, because we now have alpha. So we are in good shape that we can get the change in length. Let's look back at that picture, right? So that will give us our delta L. How will that fill in to solve for y? Well, the key is that the delta L describes how much the concrete has increased. So the hypotenuse here is going to be the original length plus delta L. So the final length is the original plus that change in length. Now we might notice that we have the original length was when it was horizontal, the new length is at this angle, and y is at a right angle, completing a triangle. So we can set up a triangle here that we have L0 squared plus y squared is equal to the resultant, L0 plus delta L. I'm running out of room here. Just fit that in. So this is something we could solve for y, right? Subtract L0 squared to the other side, take the square root, and we'll be in good shape. So let's take a look at our solution here. And I'll get my annotations out of the way. So we can get our delta L with that coefficient of linear expansion times the original length without all the sig figs written out times 13 Celsius degrees, sorry, the boxes there should just be degrees, is equal to 0.00047 meters. So that's about half a millimeter. That's not a big change in length, and that's part of why we don't tend to see this with our eyes. But with that change in length, the new length becomes 3.00047 meters squared minus the original length squared, 3 squared, and that comes out to a y of 0.053 meters, or 5 centimeters. That's about 2 inches. That's noticeable, right? That's enough that you can trip on that sidewalk. So this is something, if you go look at sidewalks, you'll notice there's just a little bit of a gap between adjacent panels, as well as bridges are designed with gaps so that when things get hot, there's somewhere for the materials to go. Now, this thermal expansion isn't just a drawback. It can also be a real benefit, and it can be taken advantage of in some designs. So one particular design is a bimetallic strip. This is two pieces of metal that are different kinds of metal glued together, basically, brass and steel here, and they have different coefficients of linear expansion. So when they heat up, the brass expands more than the steel, and so it pushes over and bends the entire strip. When they cool, the brass shrinks more than the steel, and so it bends it the opposite direction. So the difference in their expansions can cause the entire thing to move just based on the temperature. So this is actually a really simple device that's used in things like your hot water kettle or coffee maker. There's a heating coil there, and so it will, when it's connected, it will turn on the electricity, power up the heating coil, but once it gets hot enough, it clicks off. Why does it click off? Well, once a significant temperature is reached on the bimetallic strip, it bends away from the circuit, disconnects the circuit, and so then the contacts are separated, so it no longer provides electricity to continue to heat it, so you don't overheat your coffee. So this is really nifty, right? That simple little gadget, no electronics required, just taking advantage of the thermal expansion. Now, what if we have holes? Let's look at this conceptual example. Figure shows 8 square tiles that are arranged to form a square pattern with a hole in the center. If the tiles are heated, what happens to the size of the hole? Does it grow bigger, shrink smaller, or remain the same size? So I want you to think about this for a moment, come up with an answer before you go on. So go ahead and pause the video now. Right. Now this one's an interesting puzzle. Like I tend to think of it as like, okay, it's just going to sort of squish the hole out. We might lose the hole. But the thing is the outer edges of this box are not constrained in any way. And each of these squares is going to want to get bigger in all directions. So if they all get bigger, the hole is going to get bigger too. So as they all expand outward, we get a larger hole. A way to think about this is that the hole actually expands just as if there was a piece of material in there. So a hole in a piece of solid material expands when heated and contracts when cooled, just as if it were filled with the material that surrounds it. So that's pretty nifty, but just another application of this linear thermal expansion in action. And in the next section, we're going to take this linear thermal expansion and make it three-dimensional. So stick around.